Yeah, so yesterday, so basically I talked about two things. One was about symmetry of quantum field theory, and in particular, the important fact that symmetry can split. That if you divide the Cauchy surface into segments, then the symmetry generator can be expressed as a product of operators acting on each of these segments. So if you have a Cauchy surface, and if you divide into segment, then the symmetry generator can be expressed as a product of symmetry generators acting on each of these segments. There can be some subtlety at the intersection, at the boundary of this segment, which we may need to sort of address this a little bit. But modulo that, this has this kind of feature. And so the other, so this is one, so this is split property. And so by the way, how large should I write this? Is this readable from the back? Okay. What is this number? 7? Okay. So the other is that is the existence of a chord subspace. So in ADS-CFT correspondence, we expect that the full Hilbert space of conformal field theory should correspond to the full Hilbert space of the dual gravitational system. But there is an important subspace called chord subspace. And in fact, there are actually several choices of chord subspaces. And, but it has a property that, so in one choice of chord subspace, is that it describes the ground state of ADS and also some small excitation above this ADS. You can enlarge this chord subspace to include black hole states and also some microstates of black hole. But anyway, so it has this important property that if you choose the subspace of the boundary conformal field theory, then there is a well-defined subspace in the bulk. This is, well, I'm just sort of cutting the whole thing through the Cauchy surface, but it's sort of enlarged in this direction, in the time direction. The entanglement wedge regions are sandwiched between this boundary region and the corresponding Ryu-Takayanagi surface, so that so any local excitation in this region can be sort of described in terms of operators defined in this segment, and anything outside cannot. So, so this is a very important property that has been uncovered in the last 10 years or so, and this has led to a very close relation between the feature, the structure of the Hilbert space, in particular this chord subspace, and that of the error-correcting chord in quantum information theory. So these are the two important things that I mentioned in the last lecture. So Sasha has been asking what is the definition of global symmetry in gravitational side, and so this is clearly something I need to present, but this is actually a bit of a difficult task because, well, for two reasons. One is that I'm going to present the proof that there is no such thing as global symmetry in ADS. So that means that I need to define something that I'm going to prove does not exist. So that's one challenge. And the other challenge is that, well, of course, gravitational theory, there is no a precise definition of quantum theory of gravity in ADS, except in terms of dual conformal field theory. So, but we need to define something that is intrinsic to ADS gravity. So that's another challenge. So I'll try to do the best I can, and then so basically what I would like to do is to enumerate the property that we would expect to be reasonable to have for global symmetry in gravitational theory in ADS, and then show that such thing does not exist. Okay? And so what are the kind of things that we would like the global symmetry to have? So one thing is that here we are considering the case when the gravitational system has weakly coupled Einstein gravity coupled to matter field description, which can be quantized and embedded in a consistent quantum theory gravity. And in the limit when the Newton constant goes to 0, the system should become a quantum field theory with decoupled from gravity. So that means that whatever the definition we are going to make for a global symmetry in ADS has to be such that that definition reduces to that of the global symmetry of the quantum field theory. So G Newton goes to 0 limit, the global symmetry in gravity should reduce to that of quantum field theory. So that seems to be the obvious requirements that we'd like to have. And so another thing is that it has to respect property of ADS CFT correspondence. So let me first remind you some of the one of the important property. And so that is a correspondence between the state and operator. And so suppose, for example, you have Euclidean ADS, and you consider sort of half of the Euclidean ADS. Euclidean ADS is a ball, inside of which you feel the inside of the ball in terms of a hyperbolic metric. So you can cut the ball into half, and then you can consider state. You can construct a state in the ADS gravity by applying some local operator at the southern edge, south pole of this geometry. So you can act some operator, CFT operator, on the southern south pole, and then that gives rise to some kind of state in gravitational system. So that gives you correspondence between state in quantum gravity and state in CFT, which is dual to this operator. And what happens if you do that is that it's going to start exciting the bulk. But if this operator has a finite conformal scaling dimension, then the corresponding state should have finite energy. So it should asymptote to toward the boundary of ADS, it should asymptote to original ADS geometry. So that means that the excitation should somehow be localized in the bulk. So outside of some region, it should asymptote, exponentially asymptote to original ADS geometry. So the excitation would always have this kind of feature. So if you look at the Cauchy surface, Cauchy slice over here, then you have a Cauchy slice where the excitation is happening somewhere like this. Okay? So now suppose you have such excited state in ADS. So now ADS has various isometry, and each of which correspond to conformal transformation on the boundary. And one of which is, of course, this time evolution, where you start from this point and evolve in time, and that's how we get this state. Yes, you have a question.
What sets the size of the region that state is poured over? I mean, there's no light cone, right? We're in the Euclidean geometry.
Sorry?
I'm trying to understand what sets the size of the spreading that you've indicated there.
Yeah, so typical states in ADS are either some excitation of massive particles, or the black holes. And the massive particles trajectory is sort of centered in the middle, and also the black hole has finite horizon. For massless particle, in Lorentzian geometry, it's bounced back. It can go to the boundary in finite time and come back. But here we are doing this in the sort of Euclidean ADS geometry. And so therefore, the support of that would not extend to the boundary.
But how big will it be?
Sorry?
What do you have in mind for the distance scale of that white blob?
So typically, the size is typically determined by energy. So in order for this to extend to the boundary, you have to have very high energy. So the size is determined by the energy, I think. So for example, in the case of black hole, the more massive it is, the horizon grows, and it reaches towards the boundary.
So is your operator really a smeared operator that doesn't have infinite energy? I mean,
So yeah, I'm considering only finite energy excitations here.
yeah, so then it's not a local operator at the boundary.
In general, it's not a local operator. Even for, no, it's not yet a local operator. Yeah, but so far, it's not, this object, for example, black hole is not local operator. It's a local operator here. It corresponds to a local operator here. Yes?
Let's talk about a particle.
Yes.
I mean, if it was just a particle, if you wanted it to not get out to the boundary, presumably you don't want it to be out at the boundary when you put the operator in either.
So for example, if you want the graviton, so suppose, for example, I put energy momentum here, then it's going to emit graviton, and this is the kind of state I'm considering here. Right? We know that because of the state operator correspondence, any state, any finite energy state over here can be constructed in this way. Right? Do you agree?
Yeah.
So I can have energy momentum tensor, I can have various operators, conformal operator localized here, and then I create state. And if this operator has a very large conformal dimension, this can become one of the microstates of black hole, for example. Okay? So any state in ADS, gravity, can be constructed in this way. Okay? So now there are various conformal generators in ADS, and one of the conformal generators is this. So you look, if you here, the Euclidean time translation here is described by, on the boundary, the transformation which starts from the south pole and send the boundary point to the north pole. And in the bulk, this creates the global time translation. But ADS can, this conformal, the sphere in which conformal field theory is living can also be rotated. So for example, in particular, I can move this point over here. And then there is also a conformal transformation which does something like that. So this would send a bulk point. So the corresponding trajectory of the bulk point is like this. And we can reverse this. Then what happens is that in the bulk, you pick any point on the boundary, and then there is a conformal transformation which sends the bulk point toward this point. There is such an isometry transformation in ADS. And so if you act such isometry on this particular state, then this would send this state to a particular point on the boundary. So therefore, any state that you can create in this way can be sent to any of the boundary point of this Cauchy surface. And then you can obtain some local operator, right? And in fact, the resulting local operator is nothing but this original operator that you started out with. You just move this operator over here. And this is obviously true, because this conformal isometry is a conjugation of this global time translation by the rotation of the boundary sphere. So therefore, obviously, you should recover this original operator just moved over here, because I started with this operator, I did the time translation, and then I sent this operator to the boundary by the conjugation of the same global time translation going backward, but conjugated by the rotation. So therefore, you should get the same operator. This seems to be an obvious thing, this seems to be an obvious statement, but it shows that how the state operator correspondence works as a one-to-one operation. Namely, any operator can create finite energy excitation, which is approximately localized in the bulk. And conversely, any state that is approximately localized in the bulk corresponds to the local operator on the boundary. And when we talk about a global symmetry in ADS, we would like unitary operator acting on the Hilbert space of the gravitational system, which is the same as the Hilbert space of the conformal field theory, but it should act non-trivially on these finite energy states, which are of this type of state. But those, therefore, act on these local operators on the boundary. So therefore, if you have a symmetry in quantum theory gravity in ADS, then it should act on the Hilbert space of conformal field theory, and it should act non-trivially on the local operator, on the space of local operator of the conformal field theory. Okay, so have you heard something like that? Well, yesterday I used that as a definition of global symmetry of quantum field theory. So therefore, I would claim that therefore, if you try to make any reasonable definition of global symmetry in gravitational system in ADS, inevitably it has to be global symmetry of the conformal field theory. So therefore, the global symmetry of gravity in ADS has to be, one, it has to be global symmetry of conformal field theory, which is dual to that of the ADS gravity. But there are other properties that we do expect the global symmetry to have. Well, first of all, it has to act faithfully on the state or in the bulk. But we would like the definition of the global symmetry to go smoothly to that of the global symmetry of the quantum field theory in the limit where the gravitational coupling goes to 0. So in particular, that means that if you have a local excitation in the bulk, which is, so for example, in the case of quantum field theory, we require that symmetry to be faithfully represented by physical operator in quantum field theory. So namely, in particular, it has to be gauge invariant. So similarly, here we require that the global symmetry G acts faithfully on gauge invariant operators in the bulk. Yes, a couple of people raised hand. Yes, you have a question.
Is this correspondence more or less one-to-one? If we have a global symmetry of CFT, can we get a global symmetry of gravity?
No, that's why I'm giving additional conditions.
Okay.
So I haven't even finished. I have not finished my definition. So I said that if you want any reasonable definition of global symmetry for the gravitational system, first of all, it has to be global symmetry of the conformal field theory. But I'm going to enumerate that there are other conditions. Did you raise your hand?
I was wondering whether you can resolve the tension between your claim that global goes global in the boundary to the standard argument that relates gauge and global symmetry.
Yeah, so the standard argument is that if you have global symmetry of the conformal field theory, it has a gauge symmetry in the bulk. So this already seems to say, if you assume that is a statement, then this already seems to exclude the global symmetry in the bulk, because this would imply that it should be gauge symmetry rather than global symmetry. I guess that's what you're getting at. Yeah, so I'm going to do is to make this more precise. Okay, and in fact, this works for discrete symmetries and continuous symmetry, etc. You will see how it goes. Okay, so this is one of the conditions. And the other condition is that so G should act on this gauge invariant state, but it should preserve gravitational dressing. So if you have quasi-local excitation like that in the bulk, then you have to dress them by gravitational dressing, like we discussed yesterday. But we are interested in global symmetry for which the gravitational excitations are neutral. So therefore, the symmetry should preserve the gravitational dressing. And finally, we do not want to mix global. So here we are only interested in sort of inner global symmetry, in a sense that it commutes with the boundary space-time symmetry, like Lorentz, the conformal transformation or Lorentz transformation. So we would like G to act distinctly from asymptotic space-time symmetry. So this is just so that you don't get confused, you don't confuse the global symmetry with some of the space-time symmetry. So for example, suppose you have fermions in the bulk degrees of freedom, and you can ask, well, is fermion parity example of this? So in my definition, it is not a global symmetry, because you can generate fermion parity by doing 2-pi rotation on the boundary. That would also flip the sign of fermion field, preserving any of the bosonic field. So that can be that acts exactly in the same way as fermion number parity. So we wouldn't count that as a global symmetry. So I hope you agree with me that all of these are entirely reasonable requirements that we impose on global symmetry in the gravitational system. So now I would like to show that such thing does not exist. Okay? So here's an argument. So yesterday I spent quite a bit of time discussing definition of symmetry and then some of the property, and then today I already spent like first 20 minutes or so defining what we mean by symmetry in gravity. And the nice thing, good news is that once we have gone through all these exercises, then the proof is very simple. So, yes?
It's great that that's enough for you to prove that you can't do it.
Right.
But would you say that these are sufficient conditions?
That I don't know.
Yeah.
So I just enumerated all the property that you would like symmetry to be true. It could be that there are more conditions, but for my purpose, these are sufficient to prove that these do not exist. So you can impose more conditions, but that won't help it from not existing. So, yes?
Just to make sure, you are demanding it's a full symmetry of the quantum gravity theory, not just on the... You demand that it's an exact symmetry of the full
Yeah, that's right.
theory.
So this is a very important point. Namely that, so what I can prove is a symmetry which should be the exact symmetry of the full quantum theory of gravity. So for example, there can be accidental symmetry in low energy. There can be accidental global symmetry in low energy, but that should be broken in some high energy because it cannot be a full symmetry of the gravitational system. Okay? So that's why the theorem that I'm going to prove is on this corner of the diagram that I drew yesterday, which is rigorous but most useless kind. Unfortunately, all the Swampland condition lines up in the diagonal direction. So it's either rigorous but useless, or useful but speculative. And so you cannot have both, unfortunately, for now. We'd like to improve the situation. So here is a proof. So suppose you have exact global symmetry for the gravitational system in ADS. So then you must have something like a quasi-local state, quasi-local excitation in the bulk, which faithfully represent the symmetry, on which the symmetry generator acts non-trivially. Okay? So you have some excitation which asymptote to the boundary ADS geometry. Okay? So now you have to have some non-trivial generator. Now suppose you divide the boundary into segment.
Hiroshi.
Somebody raise a hand?
It's me, sorry.
Yes?
You can tell me to shut up if I'm asking too many questions.
No, you have not.
It just occurred to me that you've actually given kind of a very general definition of how to implement the global symmetry even deep in the bulk, right? Because you can just move the state out to the boundary, act with the CFT symmetry, and then move it back into the bulk. Is that what you have in mind?
Yeah, that's right. So I'm putting the state in the middle of ADS. Okay, so I'm free to do that.
But the definition of what the global symmetry does deep in the bulk is given by moving it out to the boundary, acting with a precise definition of CFT global symmetry there, and then moving it back in?
Yeah, right, yes. So you have this state which is charged, right? That's the assumption. Now suppose you divide the boundary into segment. Then, according to, since this is a symmetry, this is a symmetry of the conformal field theory also, so it has to have a standard splittability property. So therefore, you should be able to write it as a product of operator acting on each of these segments on the boundary. But because of the property of closed subspace, each of these operator can act only on these entanglement wedge associated to each of these boundary segments. So here I have drawn the picture so that it looks like any one of these entanglement wedge touches this region. In fact, in general, such local excitation has a finite size. For example, if it is a black hole, then black hole has a finite size, horizon, etc. But if you divide the boundary segment sufficiently boundary into sufficiently small segment, then each of the entanglement wedge reaches only to some small region, small distance from the boundary. So none of them would touch this operator. So that means that each one of these should commute with this operator here, this excitation here. There can be some finite size over here, but you can make the overlap between this excitation and each of these entanglement wedge as small as you like by making this division of the boundary as fine as you like. And so this means that this commute with this excitation, which is a contradiction. Okay, so that's a short proof that I could just draw it over here. Yes, Steve?
So Hiroshi, at this stage, maybe it's important to be clear, you're making a pretty strong assumption in doing this.
I have made this assumption sufficiently strong so that I can prove the theorem.
Well,
so I hope that I convinced you that, well, maybe we can discuss that these assumptions are reasonable.
Well, in particular, this correspondence between the small regions on the boundary and the states in the entanglement wedge is, that's a pretty strong assumption.
So what is the assumption you are referring to?
Basically, it's the picture you drew there. That,
okay, so where is an assumption? So here is an assumption. This is a fact of life.
There's I don't know how you can say that. That's
yes.
How can you say that's a fact of life? That hasn't been established.
Do you think entanglement wedge reconstruction is a fact of life or something that needs to be explained?
I think it needs to be explained.
Okay, so so I assume that the entanglement wedge reconstruction works. Now, what is your complaint about the entanglement wedge reconstruction?
That would be a longer discussion, but it is, I think.
So for the purpose of this lecture, and I explained the entanglement wedge reconstruction yesterday, but maybe Raphael wants to say something.
I just want to stress that you need less than entanglement wedge reconstruction in the sense that all you need is that you can't reconstruct more than the entanglement wedge. For this argument, all you need is that you can't reconstruct more than the entanglement wedge. So in fact, I think you're using a weaker...
Yeah, that's right. So it's a complement of...
And the argument for that you can't reconstruct more than the entanglement wedge is very straightforward. I mean, you would have a complete contradiction in the correspondence if you could do more than that.
Yeah, so I only need the complement of entanglement wedge reconstruction. That you cannot reconstruct states over here. I don't have to show that any excitation in the wedge can be constructed. Yes, thank you. Yes.
Sorry, so I thought our discussion of entanglement wedge reconstruction was perturbative in nature. So how are you sure that there are non-perturbative? What is the non-perturbative meaning of this statement if we are reconstructing bulk always perturbative in 1 over n?
Well, okay, yeah, so that's a good question. So that's going to be a long discussion. But so the point is that so I'm assuming that the states that I'm considering here are the ones that on which we can. So here is what we want to prove. What we want to prove is that suppose somebody give me low energy effective action, low energy effective theory, on which it is claimed that you have a global symmetry. Okay. So in order to say that the low energy effective theory has a global symmetry, it has to be that within this low energy effective theory, you can construct charged state. Right? Because you can always say that standard model of particle physics has a monster symmetry. But it's just that unfortunately none of the particles transforms non-trivially under monster symmetry. But that statement can be true in quantum theory of gravity, because if none of the states transforms non-trivially, right? So therefore, in order for the kind of things that I want to prove to be meaningful, it has to be that charged state can be constructible within the low energy effective theory. Okay? So therefore, such state should be constructible in the cold subspace, excitation in the cold subspace. So that's the kind of states that I'm considering here. Yes?
Again, I feel it's a mix between semi-classical and full quantum. This is okay in the semi-classical theory, but who told you that there are two different quantum operators that look identically?
Yeah, so what I want to do, let me try to be more precise. So what I'm trying to prove is that suppose you have a symmetry satisfying these conditions and acts on non-trivially on state you can construct in low energy effective theory. I'm saying that such symmetry transformation cannot be made into exact symmetry of the dual conformal field theory. That's a claim. So this is the same as saying that any global symmetry of the low energy effective theory coupled to gravity cannot be embedded as exact global symmetry of the quantum theory of gravity. So this is a proof. Okay. All right. So I hope that this was reasonably convincing. And I would like to make a few comments. So one is that the idea of this proof. So this is actually we realized after the fact, but is something that there is some idea in quantum information theory for which very similar argument is used. Although our result is actually more general than what is known in the literature, which is the following. So yesterday I discussed construction of the cold subspace in this simple example. So we have this kind of state that we considered, for example, etc. So you can think of this as some kind of transformation between the tensor product Hilbert space, turning that into a smaller subspace. So you have this tensor product of Hilbert space, each of which can be Hilbert space on this segment. And then on this side, you have a cold subspace, which can be excitation, low energy excitation in the bulk, for example. The excitation that is describable by low energy effective theory in the bulk. Okay? So you have this kind of map. So there is actually a theorem called Easton Cunil theorem in quantum information literature. that says that in this applies only for the continuous symmetry. Lie group symmetry. That if you have this well-defined quantum error correcting map like that, then you cannot have symmetry acting on this Hilbert space such that action of a unitary operator on each of this space can turn into non-trivial group action on the other side. So they say that they call that as this symmetry is acting transversely or something like that. And so they were able to prove this statement in the case of continuous Lie group. Now, so this you may recognize that this idea is very similar to this idea. So here the symmetry generator is acting on each of these segments. Just like each of these symmetry generators is acting on each of these Hilbert space. And the statement here is that such an action cannot realize non-trivial unitary transformation on the other side, which realizes the same group here, which is the same as saying that such operation cannot act non-trivially for the bulk operator. Okay? So they were able to show that only for continuous Lie groups. And here we were able to prove this for any groups. And the reason for that is that actually one of the crucial features of this proof is that each one of these segments preserves the code subspace. And in the case of a continuous Lie group, you can actually prove this algebraically, that if you have this kind of tensor product structure, then each one of these groups automatically satisfies the code subspace. Yes?
Suppose the low energy theory has what appears as a global symmetry. Can you tell for quantitative how high energy I should go in order to see
So this is what is like. So you have been sort of pounding on me the defect of this approach, which that's why it is on this end of this diagram. So I don't have any. So I think I have some idea of how to do it, but I don't have any prediction of when the symmetry can be broken. Okay? So the global symmetry can fail to become global symmetry of the exact global symmetry for various different ways. One is, as I said yesterday, that it can be broken in high energy by some higher dimension operators or something. Or it can be actually the gauge symmetry in disguise. But I cannot tell you when this happens. Okay? Yes?
Or relatedly, if you start with the gauge symmetry and take the gauge coupling to 0, can you see here what goes wrong in this limit G to the gauge coupling
yes,
to 0?
I'm going to tell you.
Okay.
Yeah. Okay, so here is I was telling you the analogy of this. But here I can prove a stronger theorem that it also works for discrete groups. And the reason for this is that there is an additional ingredient that in the case of discrete group also that the code subspace is preserved. So this is a sort of additional sort of feature that you can include. Yeah, you have a question.
Can you give a precise CFT definition of what you're calling the code subspace here?
What is a CFT definition of code subspace? Actually, there is, code subspace has to refer to the gravitational side in the bulk. So here, for example, I do not have an intrinsic CFT definition of code subspace in this case.
You could say that it's all CFT operators below some dimension, delta star, that is large but finite. But you may not want to do that. For example, you may want to include black hole in your code subspace, and there is a way of doing it. So that may not be the best definition. And the black hole can have pretty high energy, right? You can have, yes. So, okay. So I have a couple of more comments. So
So I don't have time to discuss this, but it is possible to generalize this definition, this argument, to include spontaneously broken global symmetry. So this can be actually pretty interesting. So you can have a situation, for example, when you can have, in the low energy effective action, you can have a scalar field. And then you can have a Lagrangian like this, minus the potential. And, but if the potential is 0, then the low energy effective action has shift symmetry. And so this can be a very useful thing. For example, there are some inflation models which makes use of this type of symmetry. But you see that this symmetry is spontaneously broken, because at least in 3 or higher dimension, the scalar field must have some expectation value, and that automatically breaks this shift symmetry, right? But you can apply this argument in such a situation also. And so in that case, you can prove that this shift symmetry has to be broken in some way. So that means that somehow there must be some higher derivative. There must be some energy scale, so that some operator like that has to be generated. Now, but for example, we don't know what lambda is, we don't know what the power is. The theorem only can tell you that there has to be such an operator somewhere. We can also generalize this argument to include discrete space-time symmetry, such as parity or time reversal symmetry. Now, but this argument does not work. There are such situations where this argument does not work, in particular in the case when this type of code subspace argument does not work. So for example, two-dimensional gravity is an example where this is not true. So maybe we already discussed it yesterday, but in 2D, there are many 2D gravity with global symmetry. So for example, the gravitational system on the string worldsheet, the string worldsheet theory is a two-dimensional gravitational system, but it can have a lot of global symmetry. For example, heterotic string worldsheet has E8 cross E8 symmetry. And the reason for that is that if there were holographic dual of two-dimensional gravity in ADS, then the dual theory should be quantum mechanics with no spatial extension. So therefore, this type of argument cannot be constructed. You have a question?
You said this also works for discrete symmetries like parity and time reversal. Yeah. This means that CPT is also not allowed?
CPT, why? CPT is, well, first of all, CPT is a theorem. I'm not sure what you mean.
Does this mean that a quantum gravity theory will not have CPT as a symmetry? That's my question.
Well, let's see. So is CPT okay, so let me see. Yeah, but I was allowing parity as, yeah. But you have a point that, let's see. Let me see what I can say about it. Right. Yeah, let me try to come up with a good way to explain this. Okay. Okay. So anyway, so let me try to address the other question first that was being asked, which is that so here I said that global symmetry cannot exist. So it should be either broken by some high energy, or it should be actually gauge symmetry in disguise. So then you can ask why gauge symmetry is allowed in this context. And the reason it is allowed is that when you have a gauge symmetry, what it means is that you must have excitation which carries gauge charge. But when you have a state with gauge charge, then you cannot just have this kind of localized excitation in the bulk, because you have to have a gauge dressing. This by itself cannot be the gauge invariant excitation, but somehow it has to be connected to Wilson line of the gauge field, and it has to end somewhere on the boundary. So this is what, for example, in the case of quasi-local excitation, this is what Kabat-Lifshitz construction tells us. So, but then end point of this Wilson line should end. So one of the edge of the Wilson line end on this local excitation, but the other end the other edge should end somewhere on the boundary. So that's where. So for example, suppose it ends on this S5, then this unitary operator at S5 commutes non-trivially with this. So that means this saves the problem. So now this operator can act non-trivially, and so everybody is happy. So it is possible, therefore, in the case of gauge symmetry, that you can have a faithful representation without contradicting with entanglement wedge reconstruction. Now, in the case of gauge symmetry, there is another conjecture for consistent quantum theory of gravity, which is called the completeness hypothesis. So I think this was probably one of the places where this was conjectured was a paper by Joe Polchinski. And the conjecture is that if you have a gauge symmetry in quantum theory of gravity, then all possible charge should appear that is consistent with the Dirac quantization in the case of U1 symmetry. And more generally, if you have a gauge group G, then all possible finite dimensional unitary representations should appear. Now, this is not obvious, and in fact, if you have a quantum field theory without gravity, there are many counterexamples to this one. There is no reason that, for example, so if you have a U1 symmetry, then what this conjecture says is that you have to have, so in general, you can have a lattice of charges corresponding to the electric charge and the magnetic charge that are consistent with Dirac quantization. And this completeness, this hypothesis requires that all the points of this lattice should be populated. You have a question?
Sorry, Hiroshi, you might already answered, but maybe I missed it. So if I try to take a gauge symmetry and send the gauge coupling to 0, wouldn't it look like the global symmetry?
Yeah, I would imagine so. Yes, yes.
But then what goes wrong with the argument? Somehow imagine you have, you would have this.
So in that case, what happened is that, so if you have low energy effective theory, suppose, for example, with U1 symmetry, then you have various charged particles, and you have a Maxwell field, right? And if you take the limit when the gauge coupling goes to 0, then the Maxwell field basically decoupled from all the charged particles. So the charged sector has a global symmetry, and but then there is additional Maxwell particles. Yes? So what's the question? So therefore, the limit of G goes to 0 is not allowed because of the problem that I just.
It's actually not just the value G equals 0.
But I think the interesting question is that would there be a lower bound? So clearly, I think this shows that G gauge goes to 0 is not allowed, right? But maybe there is a lower bound for G gauge. maybe there is a lower bound. And so that can be what is called weak gravity conjecture. So weak gravity conjecture would say that, in fact, there is a lower bound. And the lower bound has to be that there must be a charged particle so that, that it is equal to m Planck over m for that particle. So I think it is in that sense the weak gravity conjecture is a refinement of the theorem that there is no global symmetry. Okay? Does that make sense? Okay.
Hiroshi, I think the question, as I understood it, was what is wrong with this picture if G goes to 0? Like how the Wilson line disappears.
Yeah, so in the limit when so gravitational the strength of the gravitational dressing is controlled by gauge coupling constant. So therefore, in the limit when the gauge coupling constant goes to 0, this operator starts commuting with unitary operator. And then there will be no operator, no excitation which has non-trivial transformation property. So that's a contradiction. So that's how the limit, yes.
But I think you're saying that at least at the level of a rigorous argument, you're claiming the limit is just discontinuous. So in other words,
that's
you don't
right.
have an argument that it fails anywhere along the way.
For any small g, the coupling constant, there can be operator which has non-trivial commutation, so therefore it's not excluded.
I have a question that may connect with the CPT question earlier.
Yeah.
You had this argument.
I had an answer to that question. I just forgot how to construct it. Yes.
You had an argument earlier that why a global symmetry in the bulk has to induce one on the boundary, which had to do with moving the excitation to the boundary.
Yes.
And then was there an implicit assumption that the action of the boundary symmetry would keep that excitation at the same place on the boundary? Because for CPT, I don't think that would. You would not want that to be true. You'd want to move it over to the other end of the boundary or something.
Right. Yeah. So that may be the explanation. But for example, we can exclude parity or time reversal transformation. So we have to be a little bit more careful.
Has to be more.
Yes.
Yeah.
Yes. You have a question.
When you think about these charged states or their absence, do you have some type of stability criteria for them? Are they absolutely stable, or if they're metastable?
Well, I'm only talking about the states that you can define on Cauchy surface. So it doesn't have to be a time translational invariant state.
But are they absolutely stable, or?
Well, what do you mean by stable? It can be any state. So what do you mean by? It can be time-dependent state. So what do you mean by unstable?
Unstable means that it decays to.
It can be bound. It can be it can be a bound state of various particles. This can be a bound state of various particles which can disintegrate in finite time, if that's what you mean by unstable states.
So your construction includes this type of.
Yes, it does. Am I running out of time very soon? 5 minutes or 10 minutes, maybe?
Yes, definitely, since we had so many
Okay, good. Yeah, you have a question. Did you have a? Okay, good. Okay, so let me move on. So I would like to finish the proof of this completeness hypothesis, and that may be the good point to finish end. Okay. So the question is that can you prove that all finite dimensional representation appears? For example, can you prove that all the charges satisfying the Dirac quantization condition appear? And so we can actually prove this. So here is an argument. So suppose you have gauge symmetry, and then in the bulk, and then realized in this way. Now consider some finite, actually a black hole in such a geometry, and suppose you have a static black hole. Then according to Juan Maldacena, the dual of black hole geometry is a tensor product of two conformal field theory. So we can have two copies of conformal field theory. And you can have an element of the tensor product of the Hilbert space, which is sum field double. And it is given by tensor product, the sum field double state like that. Okay, so this belongs to the tensor product of the two copies of conformal field theory Hilbert space. And this state is supposed to be dual to the maximally extended ADS black hole. Now, if you have such a system, and suppose you have a gauge group G in the bulk, and suppose you have a gauge field A, then what you can do is to consider Wilson line starting from one point on the boundary and ending on the other point on the other boundary, going through the wormhole across it. Okay? So, and then you can construct the Wilson line operator, which is a trace of exponential, path ordered exponential of the gauge field. But when you take trace, of course, you have to specify representation. And I should be able to choose any finite dimensional unitary representation to define Wilson line operator. Wilson line operator can be defined for any representation. And if you have U1, you can choose Wilson line to be consistent with, well, being a representation that is consistent with Dirac quantization conditions. Okay? So now this operator acts on this Hilbert space and realize representations. And, but the point is that this operator, so what is this operator? Well, this operator is going from here to here, and there are two endpoints of this Wilson line. So therefore, this operator actually is in the representation of R, tensor product of R, the same representation R star, where this is acting on this side and this is acting on the other side. So in particular, if you act unitary operator representing the group G on the left side and conjugate it, then it has to make some representation. Right? And so that means that such representation can be realized. We should be able to realize such a representation on the Hilbert space of this conformal field theory. Yes?
But if you take a big enough representation, shouldn't you expect some kind of back reaction in the geometry?
Okay, yeah, so that's a good question. So in fact, we can actually get around this program in the following way. So suppose, so we don't have to actually consider any representation. There is actually a nice theorem in group theory that says that if you have any finite dimensional representation that is faithful, then you can use that faithful representation and then take tensor. So suppose rho is any faithful representation. And so for any given gauge group, the faithful representation cannot be too large. For example, in SU2, that you have two-dimensional faithful representation. So the faithful representation cannot grow much bigger than the dimension of the group. And if you have such representation, then you can take actually tensor product of faithful representation and its conjugation. And any representation can be constructed. This kind of things generate all finite dimensional irreducible representation of the group. So once you have one faithful representation, you can take tensor product of this, namely you can multiply that operator to the Hilbert space many times, and then can create any representation by acting on this operator many times and decomposing it into irreducible representation. So that way you can generate any representation. You can ask, well, can faithful representation appear? And you can show that so of course, when we say that the bulk system has gauge group G, then it must be that there must be at least one faithful representation. So then you can do this to generate all the representation. Okay. So this proves the completeness hypothesis. So any questions? I guess I'm running out of time, so maybe I should stop here and then.
Yes, and we can have more questions at 5 o'clock in the discussion session. And thank Hiroshi again.